Thank you very much for the opportunity to speak here. So this is the brief plan for the talk. I'll try to cover the first 4 points, and then with more, I'm not sure I'm able to get there, but I'll try to say a few words. Actually, the overall idea is that the Young diagrams, they show up in many places, many different instances, and then I'll try just to demonstrate what are the situations where they show up and why they're nice and so on. And one more thing before I start, if you have a question, just don't hesitate to ask this just right away. Okay, so let me start from the very beginning with a very simple thing. So I'll start with the partition. So what are the partitions? So we take lambda, which is a collection of positive integers. So lambda is lambda 1 greater or equal than lambda 2 greater or equal than lambda s. And this is a positive. The last one is also, all of them are integers. Maybe I just write it explicitly. Positive integers. So they are coming in non-increasing order. And why they're called partitions? So the size of partition is the sum of all lambdas. So this is the size. And the length is, so S is the length. So this is, in a sense, how you can decompose your number as a sum of several other smaller numbers. So let me give you an example. So suppose we start with a 4, which is this size. And what can we do? We can either keep 4 as it is. So this corresponds to S equals 1. Or we can write it as 3 plus 1. Or we can write it as 2 plus 2. Or we can write it as 2 plus 1 plus 1, or 1 plus 1 plus 1. Okay, so very concrete and simple. Now, how to visualize those partitions? Of course, visualization is not kind of absolutely necessary, but in many applications, it's very useful. So there are 3 different ways. So common thing is that Young diagram. So this is the visualization of partition. And as it happens in many situations, so different mathematicians are thinking about the same thing, and therefore there are different sorts of notations for one and the same thing. So here there are at least 3. The most kind of standard ones, they are right here. So there is the English notation or English style, then French and Russian. So let me give you an example. You'll see how it works. So maybe I start with the partition, say lambda being, for example, 5, 3, 3, 1.
The difference between the visualization is going to be just rotations or
right,
or something
right,
like this?
right. So it's not really important, but in some applications, this does make sense to use one or the other. So here, this is the partition of the number 12. And how would we write it here? So the English notation is like this. So you first put 5 boxes upstairs. And then you put 3 more here. And then 3 more here and 1 more here. So this 5, 3, 3, 1, this partition is seen just by counting the number of boxes in the first row, second, third, and fourth. So now the branch notation says that, okay, so we better use the coordinates. Maybe we like it. And let us so say that this point is actually here. Okay. And then we put our 5 boxes downstairs. And then 3. Oops. 3. And then 3 more. And then 1. This is strange. And then, so actually, this is mostly used in representation theory. So the branch notation is very convenient if you want to attach coordinates to your boxes, and in particular for some generalization like 3-dimensional Young diagrams. This is also very useful. As for the Russian notation, this comes from probability theory, some kind of limit shapes of Young diagrams and so on. I'm not going to talk about this most likely, but let me at least draw you the picture. So how does it look like? So you draw 2 lines here. So this is so now this special point is here. And then you put 5 boxes here. And 3 boxes here. And then 1 more box. So why do people like it? Because you see here, you have kind of shape here. So if you have a lot of boxes, you can try to think what is kind of the limit shape of the diagram. And of course, this is just a matter of your taste and the matter of the problem you are solving, but just want to mention that there are different things shown up here. Okay, so one more very basic thing here is the notion of the conjugate. Actually, I'm not sure. Well, again, as in many places mathematics, I'm not sure that Young diagrams have any link to the Young. So I don't know. I don't know. But maybe that's true. But actually, I don't know what kind of diagrams were initially used. Okay, so conjugate partition. Conjugate partition. So this is a very simple thing. Again, let me give you an example, and we'll give explicit definitions. So if I start with the same lambda being 5, 3, 3, 1, and then I draw it in the English notation, 3, 1. Then, so you remember these 5, 3, 3, 1 are rows. Now let me look at columns. So you see, here I have 4 things. And then, so I can conjugate, meaning that I'm flipping with respect to this line, like that. And what I'm getting is 4 lines, 4 boxes upstairs, and then 3 boxes here, 3 more boxes here. And then 1. So this means that if I start with this lambda, then the conjugate, which is denoted by lambda prime, is 4, 3, 3, 1, 1. Okay. And in general, what you are doing is that you are starting with your lambda being lambda 1, lambda 2 up to lambda s. And then you are looking at, so your lambda prime 1. So this is the new partition. So this is just a number of such a's, such that lambda a is greater or equal than 1. Well, clearly, this is just a number of elements in your partition, just the length of your partition. So this is nothing but s. And then you do lambda 2 prime, which is the number of a's, such that lambda a greater or equal than 2, and up to lambda prime. The largest one is lambda 1. which is the number of A's such that lambda A greater or equal than. So there's no point to go further because lambda 1 is the largest one, but so you see this is the picture. So you can forget about this general definition. This is one of the reasons why this visualization is kind of useful. So you just flip and you see what's going on. Okay, so these are kind of, this was the first part. So we do know what is the objects we want to look at. And now let's try to understand something about this. So maybe the initial thing is some kind of counting. So of course, maybe the very first question is how many partitions are there? Are here. So of course, there are infinitely many because there are infinitely many numbers. But so we see that in this example that if you restrict to some number and there are finitely many, and of course it makes sense to ask how many partitions of n are there. And let me denote by let Pn be this number. So
isn't that the belt number?
No, they are. I don't remember if there is some special name for this, but probably not. Just a name partition. Yeah. So an example is so we've seen this example that P of 4 is 5. Just count how many things are there, but you can also do the simpler thing. For example, P of 2 is just 2, right? Because you can write 2 as 2 or 1 plus 1. So there's no closed formula for Pn, as it usually happens, but there are many. What you can do is you can compute the generating function. So let me define say f of q. So I just take an extra variable q, and then f of q is p of 0 plus p of 1 times q plus p of 2 times q squared plus p of 3 times q cubed plus so on. Okay, so this is the series in the variable q, and the coefficients of the series, they're exactly the numbers we're interested in. Okay, so this is what is called the generating function. And then you may ask if there is a closed formula for this thing, and indeed there is a closed formula. So let me put it as a theorem, saying that f of q is 1 over 1 minus q, 1 minus q squared, 1 minus q cubed, so on. So if you've never seen such an expression, it could look a bit suspicious because first of all, we have infinitely many factors downstairs, and also the left-hand side is a series, and the right-hand side is a kind of rational functions. How one should understand it? Let's do it very explicitly. So what is 1 over 1 minus q? So we all know that this is 1 plus q squared and so on. So let me write it down. So this is my first ingredient. And then I have 1 over 1 minus q squared. And let's do the same thing. So just but replacing q with q squared. So this 1 plus q squared plus q to the 4 plus so on. And let me do one more. So 1 over 1 minus q cubed is 1 plus q cubed plus q to the 6 plus q to the 9 plus 4. Well, still looks a bit suspicious because the right-hand side, so each term is a series, but then you have to multiply all the guys. And why do you know that it's going to give you something reasonable? But it does. Let's just try to expand it. So I mean, for example, if you're looking at just 1, there's only one way you can get it, right? So you just take this 1, here 1, and there 1, and everywhere 1. Now, suppose we care about the coefficient in front of Q. So how can we get Q? So the Q shows up only in the first bracket. So all other guys here should be only ones. So there's Q, and there's only one. So let's go further. Q squared. So no Q squared here, here, and so on. So we are forced to take ones here. Now, how we can get this Q squared? So either from here and one here, or from here and one here. This is 2Q squared, and you can see that it's exactly the 2 we had there, and so on. So actually, one thing is to kind of understand that the right-hand side makes sense, and it's not that complicated. Another thing is to prove that indeed f of q is what we have here, just to understand that the coefficient you're getting after the expansion is exactly the number of partitions of a given. So again, it's not that complicated. I'm not going to give the proof now, but if you've never seen it, it's highly recommended to try to prove it. It's not complicated. Okay, so this is the kind of first thing we can say how many partitions are there. But let's try to be kind of maybe let me put this as kind of the first counting problem. And then there are many. I'm just giving you some examples. Let us restrict to, so suppose we want to forget about n, and let us restrict, so how many, to some box. So I mean, how many Young diagrams are sitting inside a box. So what do I mean by box? Let me draw just the rectangle. And suppose this has a rows and say n minus k columns. The reason why I'm using this n minus k probably will show up later, but this is how usually people do. So you can replace it with any number you want. So now I draw the Young diagram, which should sit inside something of this sort. Okay, so this is what I want, and I want to count how many such diagrams are there. Okay, so let me give you an example. So let k be 2 and n be, okay, so it means that my box is 2 by 2. So this is my box. And what diagrams do I like? The diagrams are just trivial one. So let me also count it. Just empty. So this is also, let's consider this as a partition of 0. So of course it's a matter of taste, but just if you want to partition 0, there's only one way, just nothing. So then you can take partition 1. So this corresponds to one box. Draw it here. So this is this box. Then there is 1, 1. Then there is the 2, which corresponds to 1. Then there is 1. And the last, which is not fitting here, but maybe I'll put it here. Sorry about that. So 2, 2. Okay, so totally we have 6 Young diagrams fitting in our box, and actually the 6 is 4 choose 2, which is of no surprise because again, it's not that complicated to see that the following statement holds true. Namely, let me put it as a claim that the number of Young diagrams fitting inside the box the size is exactly interesting. And it's not that complicated to see because actually, what is this diagram? So you start from this corner, and then you move along your diagram until another corner, which is the opposite corner. Then how many steps are you doing? You are doing exactly k plus n minus k steps, right? Because you have to move to the right and you have to get up. So there are n steps, and you have to choose where you go up. And you have to go up in k places. This gives you the binomial coefficient. Okay. There is an interesting problem actually. So you see what's the difference between this counting and the counting we did before is that we don't care about the number of boxes in our Young diagram, right? So we computed here. You see that here's one box, two boxes, two, and so on. But you can also restrict yourself to the number of boxes. So you can ask how many Young diagrams of a given size you can have inside your box. And then you can also write a generating function, and the result is something which is called Q binomial coefficients. Again, I'm not going into details here, but just saying that even in these very, very simple questions, very, very simple problems, you already see some non-trivial combinatorial algebraic structure. Okay, and maybe the last thing from this counting part, what I want to say is let us ask. So as I said, there is the conjugation operation. So any partition you can flip, and then you get something new. But of course, there are some partitions which don't change with respect to this operation. So they're called self-conjugate. So conjugation. So the question is how many self-conjugate partitions are here. Okay, so I mean, if it is, so maybe I give you an example. So how to get a self-conjugate partition. So for example, I can have, say, 4 here. And then I need to have also 4 here. And then something like E and we'll do it in a minute, right? Yeah, but so far just this is an example of self-conjugate partitions. So we do like that, and you're absolutely right. So in order to make this question kind of reasonable, right? We have to fix an n. Partitions of n are here. So the question is very natural from combinatorial point of view because you have some operation, and these are kind of invariants with respect to this operation, right? So you just look at those objects, you don't change if you apply your operation. Well, I mean, we need some kind of tool how to deal with it, and actually the Young diagram gives us very, very nice answer, which I actually like, and I learned it probably being in school, but it's very elementary. So how to answer this question? So actually the statement is that the number of self-conjugate partitions of n is equal to the number of partitions of n into odd distinct parts. So the claim is that if you want to somehow look at those partitions which are self-conjugate, you can rephrase your problem in a way which somehow looks from the first glance a bit more complicated, but the second glance very, very simple. So you are kind of looking at those partitions which have only odd parts, and they're all distinct. So let me just show you immediately why. So how to get our odd distinct parts from this partition? So let us look at the hook, which somehow comes on the very left and on the very top, right? So I mean this one. Okay, so it has 7 boxes. Let me put these 7 boxes here. 1, 2, 3, 4, 5. Okay, and then what is left? I have this another hook, which gives me 3, and then the remaining nothing really. Okay, so this gives me, starting from self-conjugate partition, I'm getting another partition of the same number, right? Because so the number of boxes is preserved, but you see that of course all the parts are odd, first of all, because this is symmetric, and they are all distinct again because of our construction. Okay, and actually you can do vice versa. So if you start with the partition which has odd distinct parts, you can get your hooks back, and then you can convert it into symmetric diagram. Okay, so maybe another example is if you start with, so let us take lambda, which is say 7, 3, 1, and then let's. So how do we get self-conjugate partition? So we start with the 7. So we have to put 4 upstairs, and then 4 to the very left. So this 7 is now taken care of. Now we have this 3, and we have to put it here inside. So we have this 3 here. And there's the remaining 1, which is in here. And so you see that we're getting the self-conjugate partition. So why should we be happy about this rephrasement? Because let me put it as another claim. So the generating function, which is given by the sum over all n greater than 0, u to the n, times the number of partitions of n with odd distinct parts, is equal to 1 plus q, 1 plus q, 1 plus q to the 5. So again, there is an infinite product on the right-hand side, but if you are interested in any concrete particle coefficient, you can expand this guy and get an answer. So just wanted to illustrate this problem is not kind of very important, but this is somehow a good illustration that you start with partitions, you have some operation, and then you draw your Young diagrams, and then you get some outcome actually already here, right? So this proof with these hooks somehow is very, very natural after you visualize, but kind of you need some job to do if you don't have this visualization. Okay. Yes.
About problem 3, can you also count how many diagrams you have basically counted in a box, which is also a diagram? So can you count how many diagrams you have in some other diagram?
This is a very good problem. Combinatorial, much more complicated. You can say something, but of course you don't have that easy answer. But many things are known. Yes. So the question was, so this claim is about the number of Young diagrams fitting inside a box, right? But this box is a Young diagram itself, right? So it has all parts equal to n minus k. Now the question was, suppose we take arbitrary Young diagram, not rectangular one, and we are asking how many Young diagrams fit inside it. The question is natural and important and stuff. Other questions? Okay, so if not, let me go further. These counting problems, they are kind of first steps in understanding what's that. But now let me move to somehow applications or how the Young diagrams are used. So there are, as I said, a vast number of those, but let me give you something which is kind of number 3, kind of one of the basics. This is about symmetric and non-symmetric polynomials. So there is a kind of, this is the, well, you can think of this as a separate kind of part of mathematics or as a part of the study of special functions, but there is some very nice class of polynomials. So let me take, so let K be some field. So whatever you like, if you like reals, take reals, complex, or whatever. So, and let me take x1, x2, and so on, be formal variables. So you can also take finite number of variables, but for today, let me take infinite. There are some reasons why one should take infinite number of variables, but many things I'm going to talk about, they are also valid for finite case. So whatever, again, whatever problem you are working with, you have to somehow adjust. So these are finite variables. Now let me consider the so symmetric functions. Functions in variables x1, x2, x3. So probably all of you have seen somewhere symmetric polynomials, right? So these are just polynomials in finite number of variables. Don't change when you kind of permute your variables. So this is a version of that, but let me give you an example so you can feel how it works. So for example, you can take x1 plus x2 plus x3 plus so on. So I have to put here all the x's I have because I want it really to be symmetric. So it means that if I have x1, I should have x100, right? So if I had finite number of variables, this should have stopped here somewhere, but this is just an instant thing. And well, you can do, say, x1, x2 plus x1, x3 plus so on, sum xi, xj, I less than j. Okay, so these are actually not polynomials in the usual sense. So these are infinite things, infinite expressions, but kind of very close to polynomials, right? So each expression is a monomial, finite monomial in x. Okay? So what is the basis? So can we, maybe I should actually also put A here, which means that we are talking about symmetric things. So can we give a monomial basis or some basis of this space? So again, let me repeat that the space consists of functions, expressions, right, in x's. So this expression is a sum of monomials, but the number of monomials can and should be in. Okay, but still, this is a vector space, actually even in algebra, so you can multiply those guys. And we're asking, can we somehow put our hands on that? Particularly, can we just describe some basis? And actually, this is not complicated. So let me give you kind of the answer. So the basis is going to be labeled by partitions or by Young diagrams. So suppose we're given a lambda. So as usual, this is a finite collection of positive integers given in the non-increasing order. And let me attach to this lambda symmetric function, which I'm going to denote by m lambda, which is actually defined in a very concrete way. So let me start with writing x1 to the lambda 1, x2 to the lambda 2, up to xs to the lambda s. Okay, so this is just a monomial. All my lambdas are positive integers. So this is some monomial in my x's. And then I start symmetrizing it, okay, plus all permuted terms. So let me give you an example so you can see how it works. So for example, if lambda is just k, so it means that s is 1 and lambda 1 is k. Okay, so then m lambda is just x1 to the k plus x2 to the k, and so on. And these are sometimes denoted by pk, and these are what I call Newton polynomials. And another example is lambda being, I don't know, 1, 1. Then m lambda is the sum xi xj, I less than j. Okay, so because we start with x1, x2, and then we start permuting these guys in order to get something symmetric. Yeah.
About the space itself, so do you require that under all symmetries, permutations infinite or finite? Or is there something that stays under every finite permutation, but not under some sort of infinite permutation?
So it should be any finite permutation, but of any size. Yeah, yeah, right. So the group is formed by all permutations, so you don't restrict the size. Okay. Yes, so this is a good question. So actually, to make the definition precise, so we have to restrict to the degree. So there should be only, so the space is the finite linear combination of these m lambdas. So in order to make this strict from the very beginning, you have indeed to say what kind of functions you are taking. But if you wish, so the thing what we did, so our space is a finite linear combinations of all those m lambdas. Okay. So now there are many. So as I said, maybe a remark. That our space of functions is an algebra. So let me again give you an example. So if you want to multiply x1 plus x2 plus so on times x1 plus x2 plus so on. Just let us take a square of the infinite sum of all the variables. So what are we getting? So first of all, we have terms corresponding to just squares. Okay. And also we have terms where you take a variable and another variable, right? So this is the, and of course we have two because we have twice such terms. So it's xi xj, I less than j. Okay. So in particular, we see that we can express this guy as a square of p1 minus p. Okay, so this is the space, and as I said, there are many questions you can study. So try to find another basis. Try to somehow find some interesting functions, some interesting polynomials in this space. And there's lots of problems, lots of questions, lots of papers and books and so on. Before we go further, let me actually, as I promised, say something about the skew symmetric story. So there is one combinatorial trick which shows up in many applications, and here this combinatorial trick changes symmetric guys to anti-symmetric. So let me show you this trick. So suppose we start with the Young diagram or with the partition, and let's do a very simple transformation. So what is the transformation? Here numbers are allowed to coincide, but let me now change it to lambda 1 plus s minus 1, lambda 2 plus s minus 2, lambda s minus 1 plus 1, and lambda s. So I add nothing to the smallest one, unit to the next to the smallest, and so on. And let me denote these guys by mu1, mu2, mu s minus 1, mu s. And we see that actually now they never coincide, right? Because we've added artificially increasing sequence, right? And then what we also know that the sum of mu i's from 1 to s equals to the sum of lambda i's from 1 to s plus s minus 1 over 2, right? Because we've added this thing. But just what I want to say that starting from a partition from the Young diagram, you can get another partition with all parts being distinct. And of course, you change a bit the sum, but you can control how you do that. So why do we care? The reason is that this allows to somehow go to the skew symmetric word. So this means that instead of considering the usual x variables, let me consider variables psi 1, psi 2, 1, such that psi I, psi j is minus psi j, psi I. Okay. So in particular, if you try to square a variable, you're getting 0, right? So psi I squares. And then you can try to look at the algebra generated by those psi's. So it means that you multiply all psi's, and you take linear combinations, and you look what is that, right? So this is somehow different to what we are used to, because we can't have powers of psi's, right? Psi I squared is 0, so you can have each psi only one time. And so the expressions we get are of the form psi I1, psi I2, psi IS, or maybe I put mu here to make it compatible. Right? And we can say that mu1 larger than mu2, so on, larger than mu s, right? Because we can, of course, we can change the order. We're getting signs, but it's okay. And we can't have anything twice. So therefore, all the elements are linear combinations of these guys. So we have infinitely many mu's. So there is no restriction on the length. S can be arbitrary, but this is what we're getting. And you can see that actually we have a kind of bijection between such kind of objects, combinatorial objects, and the partition we studied this with. I'm not saying anything serious here, but let me just write a few words. So there are kind of many theories, I would say, based on this very, very naive observation. So in physics, for example, you can see the words bosons, which correspond to symmetric case, and fermions, which correspond to skew symmetric. And let me repeat that kind of generalization and kind of proper thinking about this simple thing leads to vast number of applications. For example, there is something which is called boson fermion correspondence. In vertex separated algebra theory. Which is somehow the expansion of this observation that symmetric and skew symmetric guys are kind of related and can be easily. Okay, so of course I'm not going to talk about this, but it's just the side remark. Okay, so we are left with Tableau. And probably this is the most famous application, at least in algebra and representation theory. So namely, you can forget about everything we've been talking before. So this is a kind of separate object. Of course, not about the definition of the Young diagram. So this is just the Young diagram. Young diagrams filled with numbers. So let me give you an example. Suppose you start with the Young diagram, for example, corresponding to lambda being 3, 2, 2. So I'm using English notation like this, and then you put 1, 2, 3, 3, 1, 4, 5, whatever you want. So of course you have to specify what numbers you're allowed to put inside. But after all, Young Tableau is again very simple thing. Take your partition, take your Young diagram, and write inside some numbers. But of course, in order to get something reasonable, you have to explain what rules you're using and if there are some restrictions and so on. And indeed, there are two very, very important and I would say basic objects, basic situations where these diagrams show up. So there is representation theory. Maybe I just write combinatorics and then explain where it comes, where it's important. So the standard diagrams. So these are diagrams with the following conditions. So if you have
Standard Tableau.
thank you. Yeah. Thank you. So you have a diagram. And then you fill it with some numbers such that the number which is lower is larger than the number which is higher. And also the number to the right is larger than the number to the left. Okay, the standard means that all the signs here are 3. So an example here is say 1, 2, 3. Okay, so they go to say it again. Yes, if you want standard Young Tableau, then all the numbers. So let me say it in the following way. So far we have no restrictions. So if we define like that, so we just do it, and this is what we have. So I'll say in a minute how we use it, and then in different situations you impose different conditions. And another situation is semi-standard. And then the conditions are slightly relaxed. So then you still have strict inequalities here, but non-strict here. So an example is 1, 1, 2, 2, 3. Sorry? Yeah. I'm almost finished. Yeah. And then these are responsible for representations of SN. This is symmetric group in letters or in numbers, and this is representations of GLN, general linear Lie algebra, or general linear. Okay, so as I promised, I'm not able to about these guys, but if you have any questions, I'll be happy to. Thank you very much.
Questions we get in and whether each of the sides squared is 0 or not. Well, what is the reason for that?
Because you see, we have this condition. Let us take j equals I, and we have psi I times psi I equals minus psi psi. Yeah. Usually, so if you are working with Q-symmetric algebra, you better take field of characteristic 0, at least not 2. But in general, you can take whatever you want. So you see here, it's a bit depends on what is your space of functions you are working with. So in this case, you start with a single finite monomial, and then you don't care actually whether you use infinite permutation or finite, right? Because so if you just care where these first terms where they ascend to, so it's not important. But if you are allow more complicated space of functions where these are not linear combinations of the simple things, but maybe some infinite combination, then it could make sense. It could be different, but not in our stage.
I'm assuming the boson theory beyond correspondence is kind of the motivation to the symmetric and skew-symmetric spaces.
No, but of course it worked in different directions. So I mean, first people, yeah. First, so this is what is called the Grassmann algebra, and of course it was 100 years ago before the invention of these boson fermions, correspondence, and so on. So it's much more fundamental thing. Yeah, sure.
Well, does this could, I'm assuming it connects to physics boson fermions.
Yeah.
Say it maybe a little bit of.
Sure. You see, so what is this algebra, right? So these are those psi's, right? And we said that they commute, skew commute, right? So you can't have two twice. So this was the idea of Dirac, that you can somehow think about particles as kind of what he said. This is a kind of C. So Dirac C. What does it mean? It means that you have some particle, say electron, and then it can have some kind of energy. Energy is a number. And then you're looking at all the states, possible states, I mean, the values of the energy. But by some physical reasons, you can't have particles with the same energy. So it means that you somehow draw a picture, and then you draw all possible values of your energies. So this is 0, 1, minus 1, 2, minus 2, and so on. And then you put, say, crosses the place where you have detected the particle with the given value. And then you consider the space of all possible configurations of this sort. And this is what is called sometimes Fock space. This is some kind of basic ingredients of what they call quantum field theories. Very, very concrete from a mathematical point of view, but also used in many applications. Of course, I can't say this in 2 minutes, but this is in short. Yeah. Sorry. say it?
How is your vision?
Well, I'm not sure I can say 2 minutes about Slack varieties, but even actually, I don't know if what is the knowledge of the audience about the Grassmannians, but let me answer the question. So what is the Grassmannian? So the Grassmannian is the algebraic variety or topological space, whatever you prefer. And actually a point here, so this is the set of, so actually the set is a very rude word, but doesn't matter. So set of all k-dimensional subspaces in n-dimensional vector space. So I think most of you met somewhere projective spaces. This is an example generalization of projective spaces. So projective space is in the case k equals 1. So you take all lines in an n-dimensional vector space, and these are k-dimensional subspaces in an n-dimensional vector space. And the tricky thing is that you can look at this guy as the variety. So I mean, so far we said that kind of we are looking at subspaces, but actually you can think of each subspace as a point in some variety. So and then you can somehow try to understand what is the structure of this variety. And if you have some basis, say v1 up to vn, so this is basis of our n-dimensional vector space, then an example of a point in Grassmannian, so you can take the span of vi1 up to vik. So this is the point in Grassmannian where I1 less than I2 less than I2. So what I want to say is that inside Grassmannian, you have some concrete special points, which are just linear spans of several basis vectors. And they correspond actually to the mu's we have here. Okay. And you can, first of all, these special points play a crucial role in the study of topological and algebra geometric properties of these varieties. And somehow combinatorics of partitions and Young diagrams can be translated into geometry of these Grassmannians. And flag varieties, they are kind of collections of k-dimensional subspaces for k equals 1, 2, 3, and 4, and so on, which are embedded into each other. But this I'm not going to